Okay, notes 2.3, understanding the derivative in linear approximations. It says when we explore an application of the tangent line to a function, we call that a linear approximation. Okay, so for the exploration part, we're looking at the function y is equal to sine x. Well, if we were to zoom in far enough, and more specifically onto this part right here, we would notice that we would have a linear approximation to sine of x, where the slope appears to be 1. Okay. The slope of the tangent line at x equals 0 for the function y is equal to sine x is also 1. Remember, linear approximation, we're still talking about the tangent line, which is the slope approximation of a function. Okay. So next part is function behavior related to tangent line position. So here it has a function here. So in this case, this is the function where it labeled it A, B, and C. And here we had to approximate what the slopes are at those points by drawing those tangent lines. Well, notice in part A, we had this tangent line that goes through the point A, and we were able to use rise over run to estimate the slope to be 5. Same with this one going through B. Since it's a horizontal line, we know this slope is 0. And then with this one as well, we're able to estimate the slope of C by doing rise over run, and we get -2. Okay? A big thing here to point out is notice at slopes where we have a point, so like a sharp corner, or a cusp, or even a vertical line, all of those are points where the slope of the tangent line is undefined. Okay. So we can think of this in terms of concavity. So if we have a curve that's concave up, we know that the tangent line is going to be below the curve. Opposite, if it's concave down, our tangent line is going to be above the curve. Okay, estimating derivatives of the function at a point. So here we are given the function square root of x, and it wants us to use this alternative definition, so the limit as x approaches a of f of x minus f of a over x minus a, to find the slope at x equals 9. So first thing that we're going to do is we're going to write f of x, which is the square root of x. Then we're going to do f of a, which means we plug in 9 into x, so the square root of 9 gives us 3. From here, we're going to multiply the top and bottom by the conjugate to get rid of the radicals. And then when we do that, we notice after we simplify the numerator that x minus 9 cancels out. Okay, once we have something that cancels out and we can now plug in our limit as x approaches 9, we're able to solve our slope at that curve of the curve at that specific point. Okay, once we find that slope and the point, we can plug it into the y minus y1 equals m times x minus x1 to find our linear approximation, or that tangent line. Okay. We already kind of talked about this. Okay. So notice how we got that tangent line, right? And we were able to approximate the square root of 9.1. Well, this question says, why can't we approximate the square root of 25? Well, our linear approximation was when x is equal to 9. And 9.1 is very close to 9. But 25 is much greater than 9. So we're not able to approximate because that point is too far away from the point of tangency, which was x equals 9, which means it was outside the local neighborhood. Okay. This is just continuing off what we talked before. They said looking at the graph, if we had these different x values, what would be the approximate slope, the point of tangency, the equation of the tangent line, whether the function was decreasing, increasing, or constant. So notice that when our slopes were 0, Okay. So right here specifically, at this value here, this little arrow D, this was a horizontal line, so we knew that the function behavior was constant because the slope was 0. Okay, and feel free to try to go through this on your own, make sure you get the same type of answers. Okay, so this one says investigating slope graphs, or in other words, f-prime graphs, the derivative graphs. Okay, so number 6 says consider the function to the right. Okay, notice that the curve at the first point is at x equals 1/2. So it's talking about this first curve right here. The slope of the curve appears to be about 1. Okay, that's what this line is estimating here. Then at x equals 4, the slope has decreased to about 1/3. That's this line estimate here. Can you analyze and sketch the slope graph on the grid below? So we said that at 1/2 it appeared to be 1. So that was our first point. And then at 4 it appeared to be 1/3. So if I was to plot those points, I would have a type of curve that had a slope that was slowly decreasing. Same with problems like number 7. Notice in number 7, this is the graph of f, and this is the graph of f of x. Well, notice at these two areas, we are concave up. When we're concave up, we know that we are going to be decreasing. Okay, and then, oh, sorry, this was concave down. Concave down means our slope is decreasing. Concave up, where we are in this part, means we're increasing. So in order to draw the derivative or the estimated slope of the function, we see that this cubic turns into just a parabola. Okay, and so here we have a bunch of just rules. Okay, so this says f of x increases on the following intervals. That means the slope of the curve is positive. Okay, so where it's increasing, the slope is positive. Where it's decreasing, the slope is negative. Okay, it says f of x has a relative max and a relative min. We know that it's a relative max and a relative min because the slope at these points are 0. So that means we are changing direction here. So this would be a maximum, this would be a minimum. When we draw the tangent lines to those functions, we notice it's a horizontal line, which means the slope is 0. Okay, here it's just more practice of doing the same thing. So here we notice that this is concave up, so we should have an increasing slope. This one is concave down, so we should have a decreasing slope. Okay, same thing we just talked about. We can also find these derivative approximations from a table using that f of b minus f of a over b minus a. If when we find the derivative approximate and we get a positive number, this tells us that the behavior is increasing. If we get a negative number, then the behavior is decreasing. And if we get 0, the behavior is constant, which means this is a potential local min or maximum. Okay, so just more rules of what we just stated here. If the derivative is less than 0, the function is decreasing. Derivative greater than 0, function is increasing. We have a relative maximum if the derivative is 0, if it changes from positive to negative. A relative minimum if the derivative is 0, if it changes from negative to positive. Positive to negative, so up then down, negative then positive, down then up.